Hi, everybody. Welcome to the Grandmaster Series. I'm your host, the almost illustrious Jim Scott. Here on the Grandmaster Series, we'll be speaking with the world's leading experts in data science. We'll explore their approach and key learnings that have led to their amazing accomplishments and groundbreaking innovations in AI and data science. Before we begin, there's just a few things I'd like to point out. Anything discussed, which is publicly available, will be shared in the video summary below. If you have any questions during the video, you can submit them through chat. We'll try to provide answers throughout and at the end of the episode. And finally, please be sure to subscribe to our channel to be notified of upcoming videos in the Grandmaster series. Today, we'll be discussing melanomas and the machine learning challenge from the Kaggle competition with our NVIDIA Kaggle Grandmasters. With us today, we have Chris Deotte. He's a data scientist at NVIDIA. Chris has a Ph.D. in computational science and mathematics with a thesis on optimizing parallel processing. Chris is a 4x Kaggle Grandmaster. Next with us, we have Gilberto, better known to most of us as Giba. He's currently a senior data scientist at NVIDIA. Prior to NVIDIA, he worked at Opel, Airbnb, Petrobras, and Siemens. Gilberto had held the #1 position at Kaggle for more than 2 years. And finally with us today, we have Bo Liu. He holds a Ph.D. in applied math and statistics from Johns Hopkins University. Bo spent time working in fintech, and while doing so, was competing in his free time and earning his Kaggle Grandmaster's title. Bo joined NVIDIA in May this year and is mostly interested in deep learning competitions, especially those related to computer vision. Without further ado, I'd like to hand it over to Chris Deotte. Chris?
Hello, everyone. We're very excited to broadcast our first episode of the Grandmaster Series. Thank you for the introduction, Jim. As Jim pointed out, in this episode and future episodes, we, the Kaggle Grandmasters of NVIDIA, will present our competition victories and also present best practices on how we use GPUs and how we use different GPUs, frameworks, and stack. Now, I would love to introduce all of the Kaggle Grandmasters, including myself. But first, in case you're not familiar with Kaggle, let me briefly explain what Kaggle is. So Kaggle is an online community to engage in data science. And it has over 100,000 members. And when you visit their website, there's many things you can participate in. You can compete in competitions. You can view data sets and publish data sets. You can view code and publish code. There's a forum where you can discuss with other data scientists. And additionally, they offer some free courses and show job listings. Now, in the 4 categories that are boxed on the left, every member has the opportunity to earn medals based on either publishing quality work or doing well in competitions. And as you earn medals, then you advance your tiers. So everyone starts out as a novice in each of the 4 categories. And then as you earn medals, you can become a contributor, then an expert, then a master, and then finally, you can become a grandmaster. And you can obtain these tiers in each of the 4 categories. So at NVIDIA has hired 9 Kaggle Grandmasters. And you can see all of the names here. My name is Chris Deotte. Also on the team is, these are the screen names from Kaggle, so you can recognize. On the team is Anadero, CPMP, Bo, Giba, Dieter, Bojan, Jiwei, and Ahmet. And many of these Kaggle Grandmasters are among the top 10 in overall ranking. We also have many that are double Grandmasters. They hold a Grandmaster in 2 categories. We have triple Grandmasters, and we even have one of the only 2 quadruple Grandmasters in the world. So we have an incredibly strong team here. And we're really excited in this episode to share with you our recent victory in the melanoma competition. But before we jump into that, let me just give some general pointers. So frequently, people will ask us as grandmasters, they will ask us, how can we make more accurate models? How can we do better in competitions? So I think the best approach is illustrated in this diagram. The most important thing in a competition is to set up a very, very fast experimentation pipeline. And to do that, it's best to do the performance, set it up on GPU. And it's very important to set up a local validation, because you'll spend all of your time in this green circle, which is you'll improve your model, you'll engineer new features, you'll then train it and predict a validation set and see what your local score is. And you'll just do this over and over and over and over as fast as you can during the months of the competition. And then lastly, you'll take your most accurate model and predict Kaggle's test set. Here illustrates the software that we like to use. So our favorite software is Rapids. That is basically it allows you to do data framing and machine learning on the GPU. Also, for foundational software, you see that we use Python and Pandas and NumPy, Numba, R, CuPy, Matplotlib, PyData. Then if we're working on tabular competitions, we use Rapids, Scikit-learn, XGBoost, Pandas, LightGBM, SciPy, CatBoost. And then for deep learning competitions, here we use PyTorch and TensorFlow, OpenCV, Augmentations, Monet for 3D modeling, and we're frequently use pre-trained CNNs like EfficientNet or pre-trained transformers like BERT and its variants. So it gives me great pleasure to introduce the Kaggle's Melanoma Classification Competition, where fellow coworkers took first place in this competition out of 330 teams, and another coworker took 11th place. We had coworkers in positions 23 and 53, so we all did very well. So this competition, it was a recent competition, and the challenge was we had images from patients of lesion skin images, and we had basically had to build a model which would said whether on these images whether there's melanoma or not. So this competition had particular challenges. So there was lots of data. There was 30,000 images of large images, like 4,000 by 6,000 pixels, 10,000 tests. We also had additional external data, something like 60,000 more images. The evaluation was AUC, and the positives were only about 1.8%. So we had a very low percentage of positives, a very small sample, which makes it very difficult for your model to pick up that signal. And then additionally, we had some metadata, which you had to figure out how to incorporate into your model. So it was many particular challenges. And amongst all the challenges, you could see there, first place, that was our a fellow Kaggle Grandmaster, Bo, and his two teammates took first place. Phenomenal job. And then at 11th place, we see Jibba and his teammates took 11th place. Both are gold medals. Bo was as first place, also won a cash prize. Fantastic work, guys. So how do we approach this problem? So I was also in the competition. I came in 53rd place. My biggest competitions were I spent a lot of time just pre-processing the data. As we mentioned, you can earn medals and be grandmasters in many categories. So I was close to becoming a dataset grandmaster. So I spent a lot of time pre-processing the images. So the original data set was 33,000 train images and 11,000 test images for a total of 32 gigabytes. Some images, original images were on the top left here. They had original image sizes of different ones, but things like 4,000 by 6,000 or 1053 by 1872. So very, very large images, which contain more information than we need. So the first pre-processing step was you could center crop them, take the largest square out of the middle, and then resize that to 512 by 512. If you do that to all the images, it reduces the data set to just 3 gigabytes. You can also do other image sizes. So I had done that, and I packaged this up in a data set, and most people in the competition use these data sets. And then additionally, when you set up your local validation, you need to use a K-fold setup. So you need to break the images and the data into, say, 5 different groups. And so many images came from the same patient. So you had to be careful to make sure all of those images are within the same fold. So that's the first form of stratification. Next, there's a very low percentage of positive targets. So you want to make sure that each group, each fold has some positive targets. You wouldn't want a fold, for instance, to have no positive targets. So the second form of stratification is to balance that. And then additionally, some patients had just a few images, and some patients had many, many images. And you wanted to make sure that each fold had a good selection of both types of patients. So that is called the triple stratified K-fold. So this is another thing that I did. I packaged the images up into these 5 groups and put that in my data set. And this was used by most of the teams that competed. So it was very helpful. This data set got a lot of votes. I ended up getting some gold medals, and that gave me the Grandmaster in the data set. I was very excited about that. An additional pre-process step with the data was, so the given data, as I said, was 44,000 images. That's the train and the test. But we additionally had tons of external data, 60,000 plus images. So in total, we have over 100,000 images. But it turns out that some images are literally the exact same image. And this can create problems in your validation set if you're training on the same image as you're then predicting the validation. So you actually have to go over the whole data set and remove the duplicates. But it's trickier than it sounds because the images could be slightly different, maybe rotated or scaled. So you can't just say, check pixel by pixel. So here was another great use of rapids, which is you take all 100,000 images and you push them through a pre-trained CNN, and then out comes a vector of, say, it's just a numeric vector of, say, length 1,000 numbers. And then what you can do is you use KNN to compare these numeric vectors with each other. And it turns out that images that have similar of these vectors are similar. And you can see that in the picture here. Basically, once we have these numeric vectors, you can reduce the dimension into 2D with TSNE and plot it. And then you could see all of the numeric vectors that are similar. You can see this group 6 I've circled. Well, all those images look similar. And then this other group 7 and 2, those images look similar. So to take this one step further, if you find, 2 numeric vectors that are nearly identical, then you could actually inspect the images, and often they're exact duplicates. So this process was applied, and hundreds of duplicates were found amongst these 100,000s of images, and they were removed from my data sets and from the validation. And this helped make a more reliable validation and helped people out. All right, so that explains the pre-process. I'm now going to hand it over to Bo, who was on the first place winning team, and he's going to explain what he did to achieve that.
Thank you, Chris. Before I talk about our team's solution, I want to emphasize that Chris did a lot of contribution in this competition. So he did a lot of sharing of different ideas and the starter TensorFlow model and all the pre-processing that he just showed. And in fact, I think Chris's participation is a very important factor that this competition can be so popular. So this competition draw over 3,000 teams, which is kind of a large number for a computer vision competition. And Chris not only became quadruple grandmaster during this competition, he even became the #1 ranking in 3 out of the 4 categories.
Thank you, Bo.
Yeah, thank you, Chris. So now I'm going to talk about our team's winning solution. So the #1 key to our solution, I think, is properly set up validation strategy. So as most people already know, validation is a very important part in all the Kaggle competitions. And this is especially true for this competition. Here is why. So usually when you add external data to your training set, the way to validate is to validate based on the original data set, because the external data set may come from a different distribution. And in order to make a fair apple-to-apple comparison, you want to evaluate on the same original validation set. But this computation is different. This is because this year's data, the training data, has a very small number of positive percentage, only less than 2%, which makes the AUC metric very unstable. And unstable cross-validation score is very bad news, because even if you train a lot of models, it's hard for you to properly, accurately compare different models or compare different hyperparameters within a model. That is bad. But the good news is that in the external data, the previous year's data, the percentage of positive sample is larger. It's actually 10 times larger. So as you see, it's like almost 18%. So the way we did it is to combine this year's data and the previous year's external data, not only train on the combination of the whole data, but also validate on the combination of the whole data, which makes our cross-validation score much more stable. So this combination validation score is our primary validation score. In addition, we also track the cross-validation score on this year's data only. This is just for a sanity check. As for the leaderboard score, you can see on the screen I plotted the leaderboard score versus cross-validation score. You can see there's almost no correlation between the cross-validation score and the leaderboard score. This is because for this computation, the test set size for the leaderboard is much smaller than the training set, which means the leaderboard score is very, very noisy, very, very unreliable. And many teams in this competition fell into the trap of believing the leaderboard score too much. And in the end, when the private leaderboard is revealed, many teams drop many positions. So our team, we didn't even trust the single model's leaderboard score. We ignore the leaderboard almost entirely and trust the cross-validation score. So I think that's very important to our winning. Next slide, please. Another key to our winning is that we choose a different target than the official target. So this competition officially is a binary classification. So for each image, you are given the label is positive, means that the image has melanoma, and negative means no melanoma. But in addition, we are given some metadata. One column is called diagnosis. So diagnosis meaning like what type of skin condition an image has. So it can be melanoma and it can be something else. For a given image, it has a positive target if and only if the diagnosis is melanoma. But when the target is negative, it can be one of the 8 other things. Can be unknown, can be never, can be some other diagnosis. So in other words, the diagnosis column contains strictly more information than the binary target. So what we did is we didn't use the binary target to train the model, but we use the diagnosis to train the model. But there's a tricky thing when combining last year's data is because in last year's computation, the diagnosis and this year's diagnosis, the names, they don't perfectly match one-to-one. So what we did was to use the description on previous computations website and try to map the two. So we basically map all of this year's diagnosis back to last year's diagnosis. So in the end, we come up with 9 different labels. So basically, we treat this problem as a 9-class classification problem, and we trained it using softmax loss. And during the prediction time, the model will predict 9 probabilities, right? Summing up to 1. One of them being the melanoma probability. We just took 1 probability out of the 9 numbers, and that's our final prediction. Next, please. Here I'm showing the model architecture of the model we used. So computer vision these days is kind of a very mature field. So whenever state-of-the-art model, so-called SOTA model, is introduced, usually the author will publish a paper, and together they will open source the code, and they will also open source the model pre-trained on ImageNet or some even larger data sets for people to use, for people to try it out. And usually when the state-of-the-art model is released, it will be quickly ported into different repos. There are some TensorFlow, there are some in PyTorch, so that like Kagglers like us, we can just easily plug and play into the most recent model into our pipeline. So here, the red arrow pointed to the EfficientNet PyTorch repo that we used, but there are some other choices, and they are all very similar. So in most of the image computation, what you do is basically to take the orange box, the CNN model part, and connect and feed the image into the model, and you just remove the last layer because the SOTA model is usually trained on ImageNet, which has 1,000 classes. But for your domain-specific problem, usually the number of classes are different. Like this one, there are 9 classes. So what you have to do is to remove the last layer and change the new last layer. But you don't, for most cases, for most computation, you don't need to touch the CNN model part, the orange box part. But in this computation, it's slightly more complicated because in addition to the skin images, we're also given some metadata. And the host even set up a special price to encourage us to use the metadata. So the metadata include information like the sex and the age of the patient, and also the position in the body that the picture is taken. For example, maybe on the head or even on the leg, on the belly. So what we did is to one hard encode the categorical metadata and combine them with the numerical metadata. So there are 14 metadata. So we pass them through 2 hidden layers, then concat them to the CNN model's output before feeding into the last model. So in the end, the conclusion is that it turns out that metadata don't always help our models. And in fact, our best single model don't even use the metadata. But by including the metadata, it can give our models some very good diversity, which will help the ensemble. As for the reason the metadata didn't help the model much, I think it's because a lot of information is already embedded in the images. So these days, the CNN models, the architecture is very powerful. So they are capable of learn basically all the information or the vast majority of the information from the image. So the metadata is kind of redundant. Next, please. So if every Kaggler, all the teams have access to the same SOTA model implemented in the open source library, so how does one team distinguish themselves from other teams? So I already talked about a good validation strategy and a smart choice of target. In computer vision computation, another important key is augmentation. So in this computation, there are 30,000 images. If you include the external data, it's still less than 60, which may sound a lot, but is not considered a large data set. I think it's considered a small to medium-sized data set for a computer vision problem. So in this type of computation, it's very important to use a lot of augmentations. Otherwise, if the model sees the same positive images over and over again, it will bound to overfit to those very small number of positive images. So for the augmentations, we use a library called Augmentation in PyTorch, and it come with all the augmentation I listed on this page. And I'm showing six randomly chosen images. The top rows are the original images, and the second row are the what they look like after the augmentation. So you can see they change quite a lot. And for most of the augmentations listed here, there are some parameters come with it. For some of them, it's okay to use the default parameter, but for some of them, you need to tune it based on the data set. Different data sets may require different hyperparameters. So I'll give you an example of the hyperparameter. So so the cutout augmentation listed at the bottom refer to the black box, as you can see on 5 of the 6 image. So cutout meaning like literally cut a part of the image out and put it into black. So there are 3 hyperparameters that come with cutout. First is the size of the black square, and another is the number of black square on the image. So here I'm using only one black box on each image. And the last one is the probability when to apply this cutout. So a lot of times you don't want to apply the augmentation to all of your image. You want the model to see some original image. So in this case, I think the probability was set to 70%. That's why one of the 6 you see does not have this cutout. Next, please. Here are the training details. So compared to the things I already talked about, training detail is not that important because it's more or less standard. Everybody will do very similar things. But for the sake of completeness, I'm listing what we did to our model. So for the split, we use Chris's stratified 5-fold. I think most teams use his folding. And for batch size, we keep it constant to 64 across all models, which will be easy to tune the learning rate. And for training, we use multi-GPU with mixed precision. Mixed precision basically means you can change some less important part of your model parameter, change it into half precision, which will save some space, save some GPU space. And the multi-GPU will just accelerate the training, make the experiment faster. And for the learning schedule, we use one warm-up schedule plus 14 cosine epoch. Warm-up epoch meaning the learning rate is very small in the beginning to help the model convert. You want to use first epoch to have very small learning rate. Then 14 cosine epoch meaning that after the 1 epoch you do like a decay. The decay function looks like cosine function. That's why it's called cosine epochs. And for the optimizer, we just use the most standard one, the Adam optimizer. But the learning rate, we had to tune it based on different model. Different model may require different learning rate to converge best. And the last bullet point is the most interesting. So in most Kaggle competitions, usually you are allowed to pick 2 final submissions in the end. So what people usually do is pick one submission optimizing the leaderboard and the other one optimizing the course validation. But in this competition, as I mentioned, the leaderboard score are not trustworthy. So what we did is to have the 2 final submission, one optimizing the overall CV, the other one optimize this year's course validation. And when we train the model, when we pick the model, and when we pick the epochs, we do it different. We do it separately for the 2 submissions. So in the end, we'll have 2 ensembles with different subset of models. Next, please. So our winning ensemble ended up being the one that optimized the overall CV. Again, that's what we did differently than most teams, and I think that's the most important thing for us winning. And in that ensemble, we had 18 models. They are all trained in PyTorch. So these days, a lot of Kaggle competitions became the so-called code competition, which means that in the end, you don't submit the predicted numbers. You submit your code, and you upload your model on the server. So Kaggle will run your model on the hidden data. You don't even see the test images. So in those competitions, because Kaggle has only 1 GPU on their server, usually you are the number of model you can use in those code competitions are limited. But in this competition, is old school competition. It's not code competition, which means you can do all the prediction offline locally. That's why we can put 18 models. We can put 18 models into our final ensemble. And within that 18 there, you don't want to just train 18 of your best models and put it together. You want a lot of diversity from the 18. That's very important to have a high ensemble score. So you can see I listed all the different model backbone we use. These days, the most important one, the best ones are efficient nets. So we have different sizes of efficient net models. Another diversity comes from the input sizes. So again, thanks Chris, he created a lot of resized image, so we're able to use like different input sizes to the model. Usually, for a very large model, you can't really go too big the image size, otherwise the GPU consumption will be too large. For smaller model, you can afford to go to like almost 900 input size. So we try to mix up the different model backbone and different sizes, and finally select the combination of 18 models that give us the best ensemble score. So to average, we just took the simple average of the 18 models output. And finally, you can see our public and the private leaderboard score are both over 94 AUC, which means we didn't overfit to the public leaderboard. And after the competition, the host told me that these days all the winning the winning model already outperform the human expert accuracy. So if you give the same test images for a dermatologist to label, they will have a lower performance than the best models. Now I want to hand it to my coworker Jiba. His team also won a gold medal, and I believe they use a different approach.
Thanks, Bo, for sharing your solution. That was a phenomenal model.
Thank you.
Yeah, that's amazing. Okay. Hello, everyone. Thanks, Chris, for the intro. And I'd like to congratulate Bo and his teams for this amazing solution. I'm pretty sure this is the state of the art on melanoma detection and classification. So yeah, it was amazing. So yeah, my team solution got a top 11 on the final private leaderboard. My team was composed by 5 people, and our solution is a little bit different than Bo, especially because we made a kind of brute force attack. We built around hundreds of experiments, and I'll talk in details about our solution, but it's basically a brute force. So we use in our solution training data set from the previous year competitions from 2017 to 2020. And our validation, thanks to Chris again, is based on Chris' idea of triple stratified folds. And this is pretty good to avoid overfitting. You need to have a reliable local validation set. In our solution, we use 2 different data sets. One is the original data set that is shown on the left image on this slide. And the other one is the segmented data set. The segmented data set was built using a model trained on 2017 competition data. On that year, the competition provided the segmented of the lesion or the mole. So I trained a model on that data set and used that model to segment the 2020 image in the data set. So we ended with the original image resized to 2 different sizes, like the image in the middle. So you can see the lesion or the mole is in the middle of the image. It's a very little point on the middle of the image. There's not much resolution of the lesion. But in the right side, you can see the image with segmented, exactly the same mole segmented using that pre-trained model. We can see the mole with the higher resolution there. So in the end, we found that both of the data sets, the original or the segmented data sets, scores similar in the leaderboard, but this approach added diversity when we blended the predictions from different models. Chris, next. Okay, when I saw the brute force, that's why it's a brute force approach, because we have a combination of different models, image size, augmentations, and inference for our solution. Basically, each team member uses a different pipeline. For example, we use PyTorch and TensorFlow on our solution, and different team members use a specific one. And also, we had 15 different model architectures in our solution. We started with efficient nets from B0 to B7. We try also ResNets with different architecture size, Inception, ResNets, SE, ResNext, and dense nets. Also, we use only 2 different image size, 384 by 384 and 512 by 512. Early on the competition, we use the smaller image size and later the bigger ones. And augmentation, I can say we use a medium level of augmentation. We made some vertical and horizontal flips, rotation, crops, circular crop. That's interesting. The circular crops mimics the microscope mask in the image. We found some image with that microscope mask. Box dropout, scale or resize, brightness change, and color change. I would say compared with both solutions, it's a middle level of augmentation in our solution. And also inference time augmentation. We use that and we made some local experiments and found that if we average 10 or 20 predictions using the augmentation above, we score better than using a single prediction for each image and model. So we added some models with average of 10 augmented predictions and other models around 20 augmented predictions. If we make some combinations on that slide, for example, we train a efficient net B0 with mesh 384 size and doing average of 10 time predictions in augmentation. If we do all the combinations on that slide, we can see why it's a brute force, because we tried most of the combinations on that slide. We tried all the model architectures times the 2 image size times some different kinds of augmentations and times the 2 data sets I showed in the previous slide. So it's a lot of experiments. Chris, can you jump to next? In total, we made more than 100 experiments, but we select in the end 91 models to be part of our final solution. And from that 91 models, it's a lot of models, we made an algorithm to do a model selection. So we ended from the 91 with only 58 models in the end on our final top solution, right? And how we made that model selection? We basically used 2 algorithms. I call a correlation matrix divergence, the first one, and adversarial validation importance. So what is correlation matrix divergence? Basically, I built a correlation matrix on the train set predictions and a correlation matrix of the test set predictions. Then I take the difference between the 2 matrices. What is the idea? The correlation matrix on the train set must be similar to the correlation matrix on the test set. If the difference is 0, it means the model don't have any error or any mistake, and the model is predicting exactly the same, the train and the test set, right? But if the difference is big, probably there's some issue or some bug or something in that model that we can remove that model from the final ensemble. That's the idea. Remove models or drop models from the solution that have a big divergence between the correlation on the train and test set. This is good when the test set is different from the train set. This is good to detect models that do differently. And also, this is good to check for model consistency between train and test predictions. Also, another algorithm is adversarial validation. We train a model with the 91 model predictions to just classify if that image comes from train or comes from test sets. So the model can detect if the specific image is from train or test. If the model is finding very easily that the image is from test set, so it means the test set is pretty different than the train set, and very easy to detect that. So the idea is, try to remove all the models that are making easy to detect if the image comes from train or test set, right? So we drop that models also that make it easy to classify. So that's why from 91 models, we ended with only 58 models. Also, to remove or to drop a model from the ensemble based on these two algorithms, there's some threshold to select. So how to set the thresholds is depend by only your guess. There's no way. There's no specific or scientific way to detect that. So we set some threshold based on our feelings. Okay. Then from that 58 models, we stacked it using simple light GBM, and we added some meta features also to the light GBM. The final scores, if you trust in our CV, are those shown in the slide. The scores are pretty similar for local CV, public LB, and private LB. The private is a little bit smaller than the CV and the public, but it's expected because private images are a little bit different. And yeah, that's pretty much of our solution from the top 11. And thanks for this time.
Great model. Great job, Jibba. Great job, Bo.
All right. Guys, thanks a lot. That was really great. Thanks for sharing all the details on the Kaggle competition and how you ended up with the best of breed solution. I've got a couple questions here I'd like to ask. So the first one is around accuracy of the models. What are some things that you would need to do in order to reach significantly higher accuracy levels? Would you need more time, more compute resources, more training images? What is it that would really help push it up that next notch?
So I would say the most important thing, so in general, the most important thing is just to have more training data. But for this competition, for any competition, everybody will have the same number of images. So within the competition, so computer resource is not that important. The more important thing, I think, is the different tricks. Like I mentioned, you can tune your loss function or your target or different validation strategy. But in general, outside the competition, I would say more training images.
Yeah, I have a slightly different opinion from Bo. I think a computer resource is really important because, in my opinion, to get high accuracy levels, you need to run more experiments. And to run more experiments in the same amount of time, you need more computer resource. But also, very important is to set a good validation strategy. If you don't have a local validation strategy, a very reliable one, there's no way to improve more the accuracy levels.
Great. Yeah, and it's really important for people to understand that for the sake of this presentation, you were working within the confines of the competition rules and guidelines. And so my interest in that question is really more about broad spectrum people taking these types of solutions and applying them for broadly applicable use cases in industry. So thank you.
I also want to add that I feel that this competition was a bit unique because there was such few positive cases. To compare this, you know, Kaggle Grandmasters also did really good in this Bengali image classification, where you're classifying handwritten Bengali characters, and in that competition, a single model can get a gold. In this competition, no single model can get gold. So this competition, because there was so few positive cases, and a model can get lucky sort of or unlucky, you really needed an ensemble of a huge variety of models. And that's sort of unique. It's not always the case that you don't always need to make tons of models, but it was really necessary just because of the setup in this competition.
Oh, it's a really interesting perspective. Thanks, Chris. So the next question is, given all of your learnings from historical competitions, new technologies that have come out that you've been able to leverage, are there any competitions you wish you could go back to with these newfound learnings and try them again? And all of you basically are smiling at that question. So that's maybe we hit on a good topic.
Yeah, there's one competition early on Kaggle. Maybe it's from 2013 or 14. I don't remember exactly, but it's about to predict the weather based on the Twitter's posts. This is completely language processing competition, but it's the era of the big transformers like BERT. So I wish to know where I can reach using that big transformers on that competition to using Twitter posts to predict the weather, local weather. It will be fantastic to know.
That's interesting. That's a cautious thing between prediction and what is currently reality. It actually reminds me of the computer vision proposition that I saw, where someone created a tool that was basically interpreting hand motions to win rock, paper, scissors. And it was basically figuring out before we could recognize visually that the person was putting down paper so they could put scissors up. So that's interesting. That's cool. Chris or Bo, do you have any thoughts on that?
Yeah, I have two thoughts. So one is maturity. I think one of the big lessons at Kaggle is it teaches you not to overfit. It teaches you really what it means to, have a model that generalizes on unseen data. Because I believe every new Kaggler, loves the leaderboard, loves their name looking high, and they just keep tweaking their model to raise their name on the leaderboard. But if you do that, when your model gets applied to the private data, you generally will drop because you overfitted. So, and I made that mistake early on, and now I'm better at it. So one thing is, if I can go back, I would trust my CV more, and that would make a significant difference in some previous competitions. I would have placed better. And then additionally, I guess the reason I've been smiling is, I'm really happy to be working with NVIDIA now because I have access to so much computing resources. We have access to all these GPUs. So I'm in my mind picturing what I did a year ago and what I did today. So a year ago, I only used Kaggle notebooks. They had one P100. I'd run an experiment, let it run overnight, wake up in the morning, and it would take me a whole week to test 5 ideas. Now, I deploy ideas to multiple GPUs and I test 12 ideas a day. So I'm so excited now because I can do so much more, build bigger models, try more ideas. And, I did well in the past, but if I actually had the resources I did now, it would have been game changing. I would have been able to, do so much better. So that's why I'm smiling.
The reason I'm smiling is because I think these days the development of model architecture in deep learning in both computer vision and NLP are like so fast. So if you use today's technology and go back 1 or 2 years, you can easily win. So for example, if you take EfficientNet back to 2 years, you can easily win. And if you take a BERT back to a competition 2 years ago, you can easily beat the TF-IDF approach. So it's like bring a gun to a knife fight in some sense.
Nice.
So that's why I try to look forward to the next one instead of like going back to think about the past competitions.
Great. All right. Well, on to the next question then. What other competitions are you guys currently working on? Anything fun?
Yeah, it's a lot of fun. So currently, I think all three are working on the competition. It's a computer vision competition called it's a 3D image. The task is to use the 3D CT scan to detect some lung disease. It's called PE, pulmonary embolism, I think is what it's called. So it's unique because it's 3D. So usually when we think about computer vision, it's 2D image like the melanoma, but this one is a 3D scan. So for 3D images, there are different ways to approach. Like you can build a 3D convolution neural network, or you can take a different cut of the 3D image and fit it into a sequential model. So it's very unique, very challenging.
Yeah, I'm working on the same competition as Bo, and also I start working on the Google soccer competition. That's basically we need to code the AI from some soccer players. And the interesting about this competition is that you can see the soccer match in real time being played on the screen, on the leaderboard of the competition. So it's like a FIFA soccer game. It's pretty interesting. You can code the AI of each players, and also you can see the results of your coding directly on the screen. It's something very fun and amazing at the same time.
Sounds cool.
Yeah. And I'm working on the pulmonary embolism competition too. And I'm just like Bo, I'm really enjoying it. Because with 2D image class, so yeah, we have CT scans, so it's 3-dimensional image. With 2D image classification, it's sort of a standard process, as you know, as Bo illustrated in his talk. You basically download the pre-trained net, and there's a lot of things you have to tweak and tune, and Bo had some innovations, but there's sort of a normal path. I believe in this 3D images. It's kind of a new area. I'm doing things that's not in the literature. I mean, you have a 3D image, and then you have to extract information. And as Bo said, you can treat it like a 3D image, or you can cut it and take slices and then process slices, or there's just many different ways to tackle the problem. So it gives an opportunity to really come up with a completely ingenious, creative, sort of never done before solution. And I'm really having fun with that. I have a lot of neat ideas, and it's been really fun just sort of figuring out how to I spend more time, figuring out sort of how to approach the problem than say tuning models, and it's really, really enjoyable.
That's interesting. And honestly, I couldn't even imagine being in your guys' position, trying to compete in that competition, doing that type of work and not having GPUs to be able to use.
Yeah. So this competition would be impossible. For this competition, the data set is 1 terabyte. The training data is 1.7 million images because, for a given patient, you might have 400 images or slices. So you have 400 images. Yeah. So the data set is huge. So you can't touch it. Yeah, you can't you can't touch it without good compute.
Wow. Great. All right. And I have one final question here. So Bo or Jiba, could either of you share a little teaser with us about what our next episode is going to be covering regarding the Google Landmark Recognition Competition?
Yeah. Next episode, we will be covering the Google Landmark Recognition Competition. That one is also unique. So in most computer vision classification problem, you have a handful of classes. Even the ImageNet, there are only 1,000 different categories. But for this Google Landmark, you're asked to categorize. You're asked to classify landmark photos that the people take on their cell phones and cameras. There are over 81,000 different classes. So that's a huge number of classes. So in that competition, we use a different techniques than the one we covered. So it's mostly metric learning. But please stay tuned.
Awesome. All right. Well, Chris, Bo, Jiba, I'd like to thank you all very much for taking some time out of your day to speak with us and all the viewers. I'm sure everybody's very appreciative of that.
Thank you, Jim.
Thanks, Jim.
Thank you, Jim. Thank you, NVIDIA.
All right. You guys have a great day. And to all the viewers, I'd like to thank you all so much for spending part of your day with us and taking the time out of your busy schedule to enjoy this episode in the Grandmaster Series. For all my guests today, I'm the quiet but sometimes very noisy Jim Scott. Have a great day, and may all your data science be accelerated. Bye.